Okay, welcome back students, and as we are discussing the universal shift register, we'll see how it works. First, if you look at the circuit, in this case we have replaced at the preset point, or rather we have placed a NAND gate over there. So NAND gate also has one input common entirely, and another set has the data that is fed directly. It can be anything. It can be said to be as A3, A2, A1, A0, or B3, B2, B1, B0, or X1, X3, X2, X1, X0. So only we ensure that the output of all the flip-flops are marked as Q3, Q2, Q1, Q0. We don't use Qs for the input. Now, in the circuit, we first keep all clear as 0, all preset as 1. That ensures that the preset enable is 0 and the Q3, Q2, Q1, Q0 are 0, 0, 0, 0, and that means that the flip-flop is reset. So initially we clear out all remaining data from all the flip-flops. In this case we would be dealing with 4-bit data, and that 4-bit data ensures that we need at least 4 flip-flops. Secondly, we change all clear to 1 and all presets to 1 again, and all flip-flops get enabled. That is, if we look at the circuit, then the A inputs do not matter. That is because this is a NAND gate, and we see that when preset enable is at 1, then irrespective of the output, we see that A data values do not matter. Now, data is to be loaded serially using the data in input starting from the LSB of the number to be stored. We get a truth table that is similar to the previous case, and when we had studied the CISO and the CPO configurations, we had seen that at the 4th clock pulse we get the parallel data output, that is CPO, and at the 7th clock pulse, that is from the 4th to the 7th clock pulse, we get the output of as CISO. Looking carefully, we see that the data in is at extreme left of the screen. Now we need to see the same circuit works as CISO and CPO till the time the preset enable is 1. Now we need to understand how the same circuit works as PSO and PPO, that is parallel in, serial out, and parallel in, parallel out. Initially we keep the clear as 0 and all presets at 1. So therefore the output Q3, Q2, Q1, Q0 goes as 0, 0, 0, 0. The preset enable equal to 1, and we add data to input of the NAND gate in parallel as A3, A2, A1 and A0. So no data in the clock signal is applied. It is important to note that the moment we put in the clock, then the inputs J and K are called to perform, and the flip-flops work in a normal fashion. So since no clock is applied, so therefore the data available at the inputs has no meaning, and only preset has a meaning since it feeds in data to the flip-flop. Now it is important to note that all the flip-flops are directly connected to their preset values via the NAND gate, and we can see that the data would flow in directly to the flip-flops. Now suppose in this case we consider data again as 0101, then the preset 3 because of the bubble would be 1, preset 2 would be 0, preset 1 would be 1, and preset 0 would be 0. It is important to note that because of the bubble, the data A3, A2, A1, A0 is 0101. However, it is fed into the flip-flops as 1010 because of the presence of NAND gate. Now a low preset will set the flip-flop, as one can see from the circuit. So therefore, moving on, we see the moment we have the clock as 1, then we get the X as, the Q3 as X010, and as we can see, we keep feeding in the clock pulses, and by the 4th clock pulse the serial output is obtained. So in this case, the moment initially, even without the clock, we are able to feed data and get the data, or rather access the data from the shift registers. So 0101 is the data that we fed, and even without the clock pulse, just by changing the preset enable, we are able to feed that into the flip-flops. Hence, parallel in, parallel out requires not even the first clock pulse. The moment we start the clock, the data is already fed in and accessible to the end user, which is us. And after the 4th clock pulse, the serial output comes. So PPO takes 1 clock pulse, whereas the PSO takes 4 clock pulse. It is important to note that PSO and CPO take the same number of clock pulses. PPO takes only 1 clock pulse, and CSO takes 7 clock pulses. So comparing PPO and CSO, we find that PPO is about 7 times faster than CSO. But again, the trade-off would be amongst the cost and the speed required. So for the circuit to work as PSO, we required Q3, Q2, Q1, Q0 as 0101. So we make the clear equal to 1. We set the preset enable as 0, and to enable the flip-flops so that changes in data in and clock could be transmitted to the output. In case of parallel in and parallel out applications, that is PPO, the system does not factually operate as a shift register, since there is no clock required and no serial inputs. Each flip-flop is therefore just used as an isolated 1-bit read-write memory. Now that we have understood the functioning of the universal shift register as CISO, CPO, PSO and PPO, we move to the next logical circuits, that is the counters. Shift registers just store data and shift data left and right, whereas the counters are used to count the number of clock pulses. They can be up counter and they can be used as the down counter configuration also. So counters are shift registers that are capable of counting the number of clock pulses that have arrived at their clock input. There are factually 2 different types of counters: synchronous and asynchronous. Now asynchronous counters are those counters wherein each flip-flop gets triggered by the output of the previous flip-flop, and hence these counters are slow but accurate. Ripple counter is the simplest example of this type, and however the speed limitation does not allow them to be used for counting fast occurring phenomena. Synchronous counters do not have the problem of the speed limitation, and in this case each flip-flop is triggered by the clock in a synchronized manner, and therefore setting time is simply equal to the delay time of a single flip-flop. As we have seen earlier, the typical delay time of each flip-flop is the order of nanoseconds. Delay time refers to the time wherein the input is fed to a flip-flop and the output changes. For requirements in digital logical circuits, the delay time should be as small as possible. Even a delay time of microseconds is not acceptable in most of the circuits which involve billions of components. Hence, delay time in digital circuits should be as minimal as possible. Nanoseconds are still acceptable, but microseconds are not. So a typical ripple counter looks like this, and it is important to see that the output of the previous flip-flop is actually connected to the clock input of the next flip-flop. We find in this case that we have used JK flip-flops, and we need to see that the clock symbol states that it is performing at the falling edge. It is an edge triggered counter, and that too negative going edge. We have an active low clear. We also have input wherein both J and K inputs are at the same value. That is, they would either be in the form of 0 0 or their inputs would be at 1 1. We know from the truth table of JK flip-flop that when J and K both are equal to 0, then last state is retained. So when J and K both are 0 in this counter, then this counter does not function as a counter, rather it functions as a memory element. Since the data Q3, Q2, Q1, Q0 do not change state, they are retained. Whereas the moment both the inputs of J and K go 1, then we would always have Q3, Q2, Q1, Q0 as complement Q3, complement Q2, complement Q1 and complement Q0. So let us see how this counter works. So this counter works only when both J and K are high and each flip-flop toggles. This toggling would occur if and only if the clock input receives a negative edge. That is, the clock has to go from 1 to 0, a higher state to a lower state. No changes would occur when the clock goes from 0 to 1 or if it is a positive edge. Looking at the circuit, the symbol, the presence of a bubble as well as a small triangle ensures that it is edge triggered, and when it is edge triggered, it is negative going edge, which is going to trigger the flip-flop to change its state. So the presence of clear initially would allow us to get the output of these 4 bits or the 4 flip-flops as Q3, Q2, Q1, Q0 as 0, 0, 0, 0. And when the clear goes high, it is important to note again that it is again active low configured. So when the clear goes high, then it stops clearing the flip-flops and the counter is now ready to count. So clear goes high, the counter gets ready to count. So it is very important to note that when the first clock pulse arrives, it comes at the LSB, that is the first flip-flop on the extreme right. We see the moment the first negative clock edge arrives, the output changes from 0 to 1. The output that we measure after the first negative edge is Q3, Q2, Q1, Q0 would be equal to 000, 1. After this, it is important to note that the output of the first flip-flop, that is J0, K0, is connected as the input for the clock for the next flip-flop, just adjoining the LSB. So what really happens is that for this case, the clock input of the second flip-flop actually is going from 0 to 1. Therefore, the output of the second flip-flop would not change, as going from 0 to 1 is the positive edge. Therefore, no change occurs in Q1. Since no change occurs in Q1, hence value of Q2 and Q3 also remain the same. Therefore, after the first clock edge, the output that we get is Q3, Q2, Q1, Q0 is 0001. Now, when the second clock edge arrives, negative clock edge arrives at the LSB, then its output again toggles from 1 to 0. So, in this case, it is important to note that since Q0 changes its value from 1 to 0, therefore it is a negative going edge or the falling edge for the clock of adjoining flip-flop. That is the flip-flop just after LSB. Hence, its output also changes. But its output changes, that is Q1 changes from 0 to 1, which is the clock for flip-flop 3, that is J2 K2. Hence, output Q2 would not change, because for it to happen, Q1 has to go from 1 to 0. But in this case, it has gone from 0 to 1. Therefore, the output Q3, Q2, Q1, Q0 is 0, 0, 1, 0. At the third negative going edge to the LSB, we would see that the clock edge ensures the toggling of this LSB flip-flop, and Q0 goes from 0 to 1. But since again it goes from 0 to 1, therefore the adjoining flip-flop, that is J1 K1, does not change its state and retains the last state, which was 1. Hence, again J2 K2 and J3 K3 do not change their state. Therefore, Q3, Q2, Q1, Q0 is 0, 0, 1, 1. So hence, plotting, we can see that the timing diagram of this ripple counter comes out like this. That is, if you look at the clock at the top, that the circuit ensures that all flip-flops change their state when we have a negative going pulse at the clock. So it is important to note that the LSB changes state at all negative going edges. It toggles its value at all negative going edges, whereas the second flip-flop changes at every second negative going edge. The third flip-flop changes its state at every fourth negative going edge, and finally the fourth flip-flop changes its state after every 8th negative going edge. So this timing diagram summarizes the functioning of this ripple counter in counting decimal numbers. So, of course, in the form of binary. So if we look at the first negative going edge, we see that Q0 goes high, whereas Q1, Q2, Q3 remain low. At the next falling edge, we see that Q0 goes low, Q1 goes high, Q2 and Q3 remain 0, 0. At the third falling edge, we see that Q0 has again gone high, Q1 remains high because the clock at the input of J1 K1 has gone from 0 to 1, so no change because it's not a falling edge, and Q2, Q3 still remain 0, 0. So in a pattern for the 4-bit ripple counter, we get as 0, 0, 0, 0, first negative going edge 0, 0, 1, third falling edge 0, 0, 1, 0, then 0, 0, 1, 1, then 0, 1, 0, 0. Next falling edge you have 0, 1, 0, 1. Next falling edge you have 0, 1, 1, 0. Next falling edge 0, 1, 1. So after these 8 falling edges, the value of Q3 changes at the 9th falling edge, and we get the output as 1 triple 0. The 10th falling edge, we have the output as 1 0 0 1. Then it is 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0, and the final at the 15th clock edge we get the output as 1 1 1 1. In this way, this ripple counter is configured to count from 4 zeros to 4 ones. It is important to note that in this case it is an up counter, that is, it counts from 0 0 0 0 to 1 1 1 1. And again, if you look at how it counts, the clear goes low, then high, then Q is equal to 4 zeros, and the first clock pulse hits the LSB flip-flop Q0 becomes 1, and we get the output Q3, Q2, Q1, Q0 as 0 0 0 1. Second, of course, we get Q3, Q2, Q1, Q0 as 0 0 1 0. Third is Q3, Q2, Q1, Q0 as 0 0 1 1. For the fourth clock pulse, Q3, Q2, Q1, Q0 is 0 1 0 0. Fifth, Q3, Q2, Q1, Q0 as 0 1 0 1, and in this way, finally, at the 15th clock pulse, we get Q3, Q2, Q1, Q0 as 1 1 1 1. So the last word that is stored in this 4-bit ripple counter is Q equaling 1 1 1 1, and if we have the 16th clock pulse, then the ripple counter resets itself and we get Q3, Q2, Q1, Q0 as 0 0 0 0. At the 17th clock pulse, the cycle starts to repeat. 17th clock pulse will get Q3, Q2, Q1, Q0 as equal to 0 0 0 1. So this ripple counter is basically referred to as a binary circuit, binary logical circuit, which has, and that clock frequency this ripple counter ensures is divided by a factor of 2. Hence this flip-flop is sometimes, or flip-flop combination of the ripple counter is sometimes called as divide by 2 circuit. Each flip-flop moving from the LSB divides the clock frequency by 2. That is, if you have n flip-flops, then it divides the clock frequency by 2 to the power n. For the first flip-flop, n is equal to 1, you'll see that it changes state every alternate. That is, first clock pulse it goes 1, next clock pulse it goes 0, the third clock pulse again it goes 1, and so on and so forth. The second flip-flop changes state every second clock pulse. That is, it will be 0 0, then 1 1, then again 0 0, again 1 1, and so on and so forth. So there is a need to make a controlled counter, because the thing that we were looking at the circuit and discussing was done manually. Now we want it to be automatic. Again, the genesis of artificial intelligence is built into the circuit right from here. A control counter counts clock pulses only when commanded to do so. In the last circuit diagram, the connection high can be used as the control input. When high is 0, both J and K are 0, and all the flip-flops remain unchanged in spite of the clock pulses driving the counter. It's simple to understand that if you look at the circuit, go back a couple of slides, look at the circuit till the time this high signal, the high signal is fed directly to the J and K input of all the flip-flops, and they are shorted, means they offer the same value. Till the time J and K are 0 0, then we find that the flip-flops do not change their state, rather retain the last state. The circuit starts behaving as a ripple counter only when high signal is 1. So in this case, the high signal acts as the control input. this circuit either acts as a memory element or acts as the ripple counter. When high is 0, then it acts as a memory element, stores the last fed in data, and when high goes 1, then it starts behaving as a ripple counter. When high is 1, then both JK inputs of all the 4 flip-flops would work in their usual way. In a synchronous counter, we see that the clock is fed simultaneously to all the flip-flops. In this flip-flops, they have, or rather this flip-flop allows us to work around the ripple delay problem. So in this case, the ripple delay, how the ripple delay problem is overcome is what we would learn in our next lecture. Thank you.